So hello, welcome to final exam review. For the few of you catching this live, welcome. For those of you watching the video, I guess you're still welcome. I don't know why I put it out separately. Okay. So final exam review. I'm going to go through a very, very small PowerPoint. It is also on Vanco Hall, kind of about the final in general. And then I'm going to go through last semester's final. And as I go through last semester's final, I'll say like how I graded it and stuff and give hints and tips for this semester's final. I don't know how long I'm going to go. I'd like to keep this under an hour. Um, though doing an entire final out loud does take a little while. Um, but let's see if I can do it all. Just a reminder, I hit way too many buttons at once there. Just as a reminder, your final is Monday, May 10th, so it's within a week. It's the same idea as the other exams where it's online. You do the things on paper, take pictures and upload it. It will open at 3. Officially, your final is from 3 to 5, but I've set it to stay open until 5:15 to give you an extra 15 minutes for uploading issues. But your final itself is from 3 to 5. Don't forget you have 2 more homework assignments due. You have 1 homework assignment due Wednesday, like always, but you also have one due on Sunday because I want to make sure there's a homework for chapter 12. I do apologize, it's right before. On the final, there will be 9 questions long. You must do the first 4. The first 4 will be in order. One from chapter 9, that'll either be stress and strain, or pressure versus depth, or buoyancy. The next one after will be springs and or pendulums. The one after will be length with temp. And if I do length with temp, I might mix in stress with strain. If you see what I mean, I did a problem about Serenity, the ship from Firefly, on class on Friday. And there's one on homework about Game of Thrones for the homework due tomorrow. Or I might do ideal gas law. And if I do ideal gas law, I might work in some of the other gas equations. And chapter 12 will be you're putting some things together. What is the final temperature? So like the problems I did in class yesterday. The remaining 5 problems, you only do 4 of them. You need to mark which one you do not want graded. I'll get into how to do that in a second. But they will be in order: a projectile motion problem, a forces problem, a conservation of energy problem, a conservation momentum problem, and a rotational problem. What the setup is going to look like for that is when you get to those ladle problems, I will have both a text box and a spot to upload. And it just says if you plan on skipping, write skip here. And basically that's it. Whatever problem you're going to skip, just write skip in it or something else. So make it obvious. Put something in this text box and I'll know to skip that problem. There's kind of some issues with Vanco Hall and grading doing that. I've worked out how to get around it. This is me talking about how I'm going to get around it in detail. But the short version is when you're done with the exam, if you look at your grade like in the actual exam section, like if you hit this and your grade shows up afterwards, your grade shows up like over here, the number might not be quite correct because it's out of 200. And it's going to deduct some points. But your grade in the grade book will be correct. I figured out how to get a workaround. Also, I really recommend you make an equation sheet. You can theoretically look up everything for every slide. It is open notes, but that's going to take a shit ton of time. I recommend making something you have to have your equations and how to solve problems in front of you to save you time. All right, any questions about the exam in general? Okay. So these are the equations. You've seen a lot of this before. Definitely unit conversions will show up in there somewhere. And we have our kinematics. Although really, I'm not going to do straight up kinematics. I will do projectile motion. Well, projectile motion uses the free fall equations in y plus the equation x. Really, that box is the big thing for those. But keep in mind, you would need to deal with vectors as part of that. One of the problems will also be our forces. Know your F equals ma, know how to deal with friction. You can also, we'll get on here. As I said, there'll be conservation of energy. I might involve rotational, I might involve springs, so be prepared. Momentum will be there. It could be two-dimensional, but it won't be. It'll be single-dimensional. And for rotational, we have the rotational kinematics. We have torque. We have centripetal acceleration, and we have angular momentum. That's all the old stuff. There's nothing new in any of that. The new stuff, chapter 9, know how to deal with Young's modulus, shear modulus, and bulk modulus. Also known pressure as a function of depth, and pressure as force over area, or Pascal principle. It could be any combination of those. I could also ask a problem on buoyancy, where that's the equation for buoyancy. B minus W equals rho fluid minus rho object GV. For chapter 10, it could be springs. It could be pendulums. And there's also the equations that work for both springs and pendulums. There's also equation for waves, but it won't be waves. For chapter 11, know how to deal with temp expansion. If I do temp expansion, it might go back to that F over A equals Y delta L over L naught equation. Also know your gas equations. And for the fourth problem, we'll deal with heat. On this, there's one equation here you have yet to see it, or two equations you've yet to see yet. We've yet to cover these equations, this one and this one. They'll be on the homework. I'll cover that tomorrow, but they will not be on the exam. Any questions on that? Okay. Let's look at a practice exam. So as I said, this is last semester's exam, fall 2020. It's the same one as the one that is on Vanco Hall that I had opened right here. So if I go in and go to problem 1, you'll see the same problem. The solutions are going to be posted. Actually, they're already posted. But let's go through. The first problem says, Patrick from SpongeBob SquarePants appears to be a Pisester brevifinus, or pink sea star. On average, they have a mass of 4.5 kilograms and a volume of 0.00302 meters cubed. Assume Patrick is standing still on the ocean floor, surrounded by salt water. What is the normal force while underwater? Assume he has the same mass and volume as the given values. Okay, if I want to find a normal force, that's a force problem. That's good old F equals ma. And if he's just standing on the ground, we're going to say he has no acceleration, that A is 0. For the record, I'll give points as I go. 3 points for F equals ma, which means I need a free body diagram. What I can do is say if he's standing on the ground, he'll have the force due to gravity, and he'll have his normal force. But he's underwater. And let me mark those up. Instead of writing mg, I'm going to put weight. I'll come back to y in a second. We have normal force. But he's underwater. If he's underwater, he will feel a buoyant force. A buoyant force upwards. Buoyant. That's a B. This doesn't look like one. That's 3 points here, 1 for each arrow. And so what I can say is that up minus down, my force equation would be the buoyant force plus the normal minus the weight. And since this F equals equal, that equals 0. I gave, wow, I can't read my handwriting. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I'm not sure if I gave these are 2s or 1s. I'm going to put it for a 1 for now, and then I'll go back and check. 3, 4, 5, 6, 7, 8, 9, 10, 15, 16, 17, 18, 19, 20, 21, 22, 23. Nope, these are all 2s. Now my goal is to solve for the normal force. So I'm going to take everything that isn't my normal force and put it to the other side. And that means the normal force is the weight minus the buoyancy, which is the same as the normal force is negative buoyancy minus weight. Now, this first problem, as I said earlier, and I forgot to do it, is going to be something from this from chapter 9. Either be all of that or all of this. It'll either be length elongation, or it'll be density or pressure as depth, or it will be buoyant force. Length elongation is normally pretty obvious. I talk about stretching something. If I do pressure as a function of depth, it'll be just, what is the pressure here? But I'm asking about forces. If I ask for forces are going to be buoyant force, especially if they're underwater, at least for the first problem. When you get buoyant force, you'll always end up with a B minus W term, like I did here. And what you'll do is you'll say that B minus W term, you'll just plug in that it's rho fluid minus rho fluid minus rho object GV. 5 points for that equation. Now in this, and I'm going to go back to the center, rho fluid, that's the water. And the object is this Patrick. Now, if I look at my knowns, I don't know Patrick's density, but I do give his mass and volume. Keep in mind that density is mass over volume. And therefore, his density is just going to be his mass, 4.5 kilograms, over his volume, 0.00302 meters cubed, which is 1490.07 kilograms per meter cubed. He is dense. +3 +2. And therefore the normal force is negative 1020 minus 1490 times G times V. Any questions? Once again, it might not be the same. In fact, it won't be the same. The other things I could do if I don't do buoyancy is, once again, pressure as a function of depth, or something with Young's modulus. If you want example problems of those, look at the practice problems for chapter 9. There's stuff with Deep Sea Challenger. There was pressure as depth. In the class I did someone, the Deep Sea Challenge pressure as depth. Also, I worked Young's modulus into that too. Look at that problem. That's a good one to study. But go through problems, you'll find other ones like it. Questions? Okay. The second problem will be springs or pendulums. Either way, if I do springs or if I do pendulums, no matter what, these equations right in here, these springs and pendulum equations, will come into play. Can I make this a little bigger and still fit? These equations will come into play either way. So be prepared for those, definitely. But past that, as I said, I could do springs, I could do pendulums. Last semester, I did a spring. And what I say is the match of Super Smash Brothers from exam 2 is still going on, but now Min Min is hanging from a spring arm off the edge of the level. Due to the spring-like nature of her arm, she is bouncing up and down in simple harmonic motion with a period of 0.6 seconds. Okay, springs or pendulums, doesn't matter which one I do. Period will probably show up in some form, if not period frequency. period, which is capital T, in this case was 0.6 seconds. And I said a maximum displacement from equilibrium of 0.5 feet. Okay, I will be working unit conversions on here. Be prepared for them. I don't want to work in feet. If this is 0.5 feet, I need to cancel out feet and get meters. Well, 1 meter is 3.28 feet. And what I could say is 0.5 feet is 15240 meters. Sticking to my point breakdown, I always give 5 points for a unit conversion. And I say the spring constant of min-min's ohms is 9580. What is her mass? Huh. There's a mistake in the solutions. That's amusing. I wrote down my knowns, and I wrote a known as a mass of 30.6 kilograms, which that number came from nowhere. It's because I probably copy and pasted this process from a different problem and just forgot to fix that. That's not even the final answer. It's just I wrote that instead of K equals 9580. I'll need to fix that. So if I give you period directly relates to mass and spring constant for a spring. What I can say is that the period is 2 pi square root of m over k. Those 3 points. Now, that is true for a spring. If I do a pendulum, it's more likely to get the t equals 2 pi square root of L over g. But as I said, it could be either one. I might do springs again, use same equation. I might do pendulums. If I do pendulums, you're going to be looking for, as I said, this guy. What I will say is I will not make these show up, these equations, because those equations you have to have your calculator in radians, and that's just a dick move. Keep your calculator in degrees for the entire thing. So if I want to solve this for m, what I'm going to do is I'm going to divide both sides by 2 pi. And then I will square both sides. And if I multiply both sides by k, I get that t or m equals t squared k over 4 pi squared. Or 0.6 seconds squared times 9580 newtons per meter over 4 pi squared. You even had the period wrong at the top. I read the period was 1.53 seconds. 87.4 kilograms. Part B, what's the max velocity? I don't care if I ask for springs or pendulums. Anytime you see max velocity, if you see max velocity, V max equals omega A. That's going to be how you do it. Now, omega can be solved multiple ways. For both springs and pendulums, omega is 2 pi over t. But for at least a spring, we can also say it's the square root of k over m. If it's a pendulum, it would be the square root of g over L. But either spring or pendulum, you can use 2 pi over t. I can say that omega is just 2 pi over 0.6 seconds, where 2 pi divided by 0.6 seconds is just 10.472 radians per second. 3. I gave 3 points for either of these equations. 2. And I'll plug that into this guy. And so V max equals omega 10.472 rad per second times the amplitude. Now I say max displacement equilibrium is 0.5 feet. That was this number up here. That means our amplitude is 0.1524 meters. I converted it earlier. 1.6 meters per second. If I do a pendulum, look out. I might not give amplitude. I might tell you the distance for the full sweep. Make sure you cut it in half if you need to. Other things I often do in these problems is I also often ask for max acceleration. So be prepared for that. Sometimes I also ask for frequency. Well, frequency is just 1 over period. And that's what I did on this exam. As I said, I'm losing people. I might do pendulums instead. I might do springs instead. If I do springs, the grading logic will be pretty similar. Or if I do pendulums, grading logic will be pretty similar. But one thing to be prepared for is really, if I do pendulums, it's going to be basically the same. It's just you replace this equation with this equation. It's mostly the same. Not much difference though. Any questions? Okay. The third problem will be from chapter 11. This gets into thermodynamics. Ooh, and you guys are going to get lucky with something I'm about to do. The third problem will either be these guys or these guys. If I do the first set, that'll be length elongation. That'll be something like we heat up a bow, how much longer does it get? Go look at the homework. You have a problem where someone from Game of Thrones sets a sword on fire. How much longer does it get? If I do those equations, there's a real high chance that the Young's modulus equation will show up also. Or pressure is, or P equals F over A. I actually don't remember what this problem is on the exam for this semester. But there's also a really good chance that I don't do that and instead go gases. Last semester, I went gases. And I say, Monkey D. Luffy from One Piece can inflate himself like a balloon to a volume of 6.31 meters cubed by inhaling 1.6 times 10 to the 20th molecules of air. If the air is at 23 degrees Celsius, okay. If I give you any equation with a delta T, so like these temp ones I was just talking about down here, Celsius is fine. Any equation just with a T in it, you gotta work in Kelvin. If I tell you 23 degrees Celsius, I'm gonna need to convert that to Kelvin to get 296 Kelvin. 2 points just for that. I don't give it 4 points for a unit conversion. And it says, what is the pressure inside him? If I give a problem with gases for the third one, ideal gas law will show up. The ideal gas law states PV equals NKT. If I want to solve for the pressure, that just means I'm solving for P. That P equals NKT over V. Well, 5 points, 5 points. So it is 1.6 times 10 to the 20th times 1.38 times 10 to the negative 23rd joules per Kelvin times 296 Kelvin divided by 6.31 meters cubed. I switched pen colors at one point without even noticing. 1.04 times 10 to the 5th. Now, usually when I do a gas problem, I don't just ask ideal gas law. Reason why is that's only so much, I only gave 9 points so far. I need to give 25. So I got to make sure there's other stuff. If I go gas, I'll probably include some of the other stuff, which could mean the energy of one molecule. It could mean the energy of all the molecules. It could mean the velocity of the molecules. Last time I said, what is the total internal energy? Total internal energy is U, which is 3/2 NKT, which was 5 points. And so it would just be 3/2 N, 1.6 times 10 to the 20th, K, 1.38 times 10 to the negative 23rd joules per Kelvin, T, 296 Kelvin. Three points. I also asked for the velocity. How fast on average is the air molecule traveling at? V equals the square root of 3kt over m. Keep track of your v's. Lowercase v is velocity, capital V is volume. Make sure you don't mix them up in these problems. That's a common mistake. And velocity and volume have very different meanings. As I said, if I don't do gases, expect this stuff. If I do that stuff, be prepared for maybe some things from chapter 9 showing up. Questions? Okay. The fourth problem will be from the stuff that we just covered in class. It'll be solve for T final. It will be. I'm mixing some stuff, solve for T final. I might involve ice. I might not involve ice. Now, before even reading this, I'm looking at the picture and I say, okay, this is probably going to involve ice because the picture has ice in it. Pictures are useful. But let's read it. To try to cool it down, a person surrounds a room temperature can of beer with 0.5 kilograms of ice at 0 degrees Celsius. Okay, we're going to include ice. Assume the beer in the can itself, which is made from aluminum, starts at 20 degrees. If left to go to equilibrium, okay, let's just start writing down some things. So I say we have 0.05 kilograms of ice with a temperature, ice initial, of 0 degrees. We're going to mix that with a beer with a can. So we have a temperature of a can initial of 20 degrees, but also the temperature of beer initial is 20 degrees. If left to go to equilibrium, what is the final temperature of the beer after the ice is melted? And then I give a bunch of masses. I'm not going to bother writing down all the masses, specific heats. Here's what we know. This was actually a slightly harder problem than I normally do for a temperature one, by the way. I decided to be mean last semester. But no matter what, when solving these, Q total is 0. And, oh, 1, 2, 3, 4, 5. Okay, I didn't write numbers. I just put circles. That's 5 points right there. Now, Q total, 3 things are happening here. What this is we have Q of the ice melting. We also have, once the ice melts, the ice becomes water. So we also have Q of what was once ice and is now water heating up. And then we have cooling, a can, and beer. Now, last time in class, I only did it with 2 things. This one has 3. It doesn't really add up too much more complication, just some annoyance. As I said, I was kind of mean last semester. I think I was in a bad mood when writing the exam. Or I just really wanted a beer, one or the other. But for this ice melting, that involves melting. Anytime something melts, we say has amount of energy because mass times the latent heat of fusion. The other 3 involve temperature changes. When you have temperature changes, Q is mc delta T. And what I'll do is I'll work these all out. And I'll say, okay, ice melting. That'll be massive ice, latent heat of fusion of ice. Waddle. Well, once it melts, it becomes waddle. It still has the same mass, has specific heat of waddle, and it'll be T finus minus T initial of the ice. But the initial of the ice was 0. So you know what? Let's just not even write it down. It's 0. We then have the can. The mass of the can, C of the can, T final minus T initial of the can. And we have the beer. The mass of the beer, C of the beer, T final minus T initial of the beer. And all of this equals 0. I gave 5 points for this. Now let's take a look at what I got so far. I got 20 out of 25 points without doing any math yet for setting this up. This is important. I care about the setup. I will not give full credit if you do not show full work. But let's actually try to solve this. I want to solve for T final, which is in 3 different spots. It is here, here, and here. So I'm going to factor through all of my parentheses. Then I'm going to take everything without a T final in it, which is this, this, and this, and I'm going to move it to the other side. This will allow me to factor out a T final from this side. I don't feel like writing that line again. And then I'll divide both sides by everything in parentheses. Oh, I did IC. I see. I was trying to be consistent. I'm going to do something I normally don't like to do, but I want to try to get through more problems. I'll then plug all those numbers in. This is what happens when I go lazy about writing numbers out. And solve. This is of note. Multiple people every semester jump to this last line. Because these problems often solve the same, they jump straight to this. If you jump straight to that, you have a maximum possible points of 5 points. I want to see the steps going up to it. Once again, this one involved ice, also involved 3 things. I'll never go more than 3 things. I often only do 2. I might not include ice. If you want to see a problem without ice, I did one yesterday with a blade. On the homework, there was Snoop Dogg drinking gin and juice. I'll do a practice problem on Friday when we get there. Any questions? That is all of the new stuff. Everything else is old things we've done before. It is only 12:35, so I plan on continuing. I mean, you can stop watching / sign off if you want, but I will keep going. But any questions on the new stuff in general about this exam? Okay. So, last semester, my next problem was a scene from Lord of the Rings. This is in Two Towers. That during the Battle of Helm's Deep, Aragorn picks up Gimli and throws him. To which Gimli's last things he yells is, "Don't tell the elf." So, what I say here is, let's say Aragorn picks up Gimli and throws him at 23 miles per hour. Okay, hold on. He throws him at 23 miles per hour. That's a unit conversion. I need to know that 1 mile is 1,609 meters, and 1 hour is 3,600 seconds. So 23 miles per hour is actually 10.2797 meters per second. I don't have the stats with me. I should have opened those up. While I'm gonna start solving this, I'm gonna open up some stats. As I said before, you don't have to do. You can skip one problem. This might be interesting, so I'm gonna find it. 0 people skipped this problem last semester, just so you know. 0. Not one. So he picks him up, throws him at that speed at 20 degrees. Anytime you have any vector at an angle, you always want to break the components. I'm going to turn this v naught into a v naught x and a v naught y. Well, v naught x is v naught cosine theta, and v naught y is v naught sine theta. Really, x component is always going to be x, y component is going to be y, unless we're looking at a ramp problem. So we'll just do, I'm going to round this for now. I'm going to use the whole number, but I'm just going to not write the whole number. 10.3 meters per second, cosine of 20 degrees, and 10.3 sine of 20 degrees, which is 9.65978 and 3.51587. I didn't have to look, I know this grading. Plus 3, plus 3, plus 2, plus 2. Now, projectile motion, this will be part of the projectile motion problem. I can guarantee that. Past that, projectile motion problems come in 2 flavors. I either give you x and ask for y, or I give you y and ask for x. How to solve is basically the same either way. Now, in this one, I say y equals y naught. What is x? This is, y. You can define 0 if you want, so I can just say y naught is 0. I want x. That's where the question mark is. As I said, the other thing I could change is I might go the opposite way. If I know y, I will start with the y equation. The y equation being this guy right here. Y equals y naught plus v naught yt minus 1/2 gt squared. Y equals y naught, so it can be simplified to 0 equals v naught yt minus 1/2 gt squared. Which means 1/2 gt squared equals v naught yt. Divide both sides by t. 1/2 gt equals v naught y. Multiply both sides by 2. Divide both sides by g. The secret for the projectile motion problem, I didn't say this out loud and I should have, is always going to be whichever thing you know more of, use it to get t, plug it into the other. I knew y here, so I'm going to use y to get t and plug t into x. If I go the other way, if I give you x and ask for y, if I give you x and ask for y, use x to get t and plug t into y. See, now that I know that equation for t, I can solve for it. 2 times 3.51587 over g equals 0.716793. And I'll just plug that into my x equation. X equals v naught xt. Obviously, it won't be an identical problem, but it will be projectile motion. It will involve this. It will involve this. It will involve this. It will involve that. What you're going to need to do is get your x and y components. Once you have them, use one of either the x equation or the y equation to get t and plug t into the other equation. Any questions there? Okay. Problem 6 will be forces. Now there's a lot I can do there.
Sir, I have a question.
Oh, sure. What's the question?
Let's say there's a 2-part problem and I got part A wrong. Would you hit me again for part B?
No. I would plug your numbers into the calculator and give you full credit for B, assuming you will, and only hit you if you got like, the audio part.
Okay, thank you.
No problem. So the next problem will be a force problem. Only 2 people skipped it. For the record, 22 people took the exam. Only 2 skipped problem 6. Problem 6 will be forces. So the one thing I can guarantee is that it will be based around F equals ma. I might involve friction, I might not. You might need these guys, you might not. I often include friction, but I don't always. There's a lot of ways I can go here, though. There's a lot of different problems we did. There's a lot of things you can practice. But no matter what, it will be F equals ma, and more importantly, a free body diagram. What I really want to know you can do is you can look at a situation, make the free body diagram, and make the force equations from it. That's the important thing to me. So, what I got is the Dungeons & Dragons 5e Druid spell Thorn Whip creates a vine which whips out and grabs someone, pulling them towards you. Let's say a druid grabs a kobold with a created vine, pulls them with 500 newtons of force at 15 degrees. Okay, right there. Well, actually, I'll come back to that. But it's at an angle. We have to break that up. The kobold has that mass. What's its acceleration? If I'm going to solve for anything, I need to do my forces. And what I can say is this whip pulls along that value. And so my tension is like that. But I can say what other forces are acting on this person. There's gravity. He's on the ground, so there's a normal. And I say assume it never leaves the ground. That's coefficient of kinetic friction. So there's friction. And so I'll say normal mg friction. It'll be kinetic friction because they're being pulled. Now, I might do a ramp problem. If I do a ramp problem, be prepared for those. But on this one, this is a nice flat problem. An F along negative X, N along Y, mg along negative Y. But that T is up and at an angle. It's not to the right. It's not up. It's somewhere in between. Any vectors that are at an angle, you want to break the components. I'm going to take this T and turn it into 2 forces. One straight along X, and another one straight along Y. Where I'll call these Tx and Ty respectively. Where Tx is T cosine theta and Ty is T sine theta. This was 2 points for each one. And for the record, that free body diagram was 4 points because I gave it for the original T, but I just haven't marked it. Now I say, what is the acceleration? We're solving for acceleration. We're going to be using F equals ma. But F equals ma is really 2 equations. It's the sum of forces in X is mass times the acceleration in X. And the sum of forces in Y is mass times acceleration in Y. But in there I said, assume it never leaves the ground. If it had acceleration Y, it would either go off the ground, it'll go into the ground. So I can assume there's no acceleration in y. And I'll make my equations. X is always everything to the right minus everything to the left. That means my x equation is t of x minus f of k equals ma. And my y is up minus down. N plus ty minus mg equals 0. Or the other ones. Now this a, that's what I want to solve for. And I mean, I could solve for this a. I'll just divide both sides by mass. That a is t of x minus f of k over m. But I got to go a little further. See, t of x, I know is t cosine theta. And f of k, well, I don't have a value for f of k. But that's the force of kinetic friction. The force of kinetic friction, as I have, wait, oops, in that box, is mu of k times the normal force. I don't know the normal force, though. Oh, that equation, for doing that simplification, that was 3. If there's a problem with friction, how to get the normal force is you use your y equations. See, the only other place I have n was right here. And I can use this to get n. See, if n plus t of y minus mg equals 0, that means n equals mg minus t of y, or mg minus t sine theta. And I can solve for it. 18 kilograms times g minus 500 sine of 15. 47.17. And plug it in over here. 500 cosine of 15 minus, what's mu of k? 0.56. 47. Now, like I keep saying, it won't be exactly the same problem on your exam. I might include a ramp. I might put it in equilibrium. I've done a lot of problems with force, and I've given you a lot of problems. Go through them. Check the homework. But really, the trick is F equals ma and make a free body diagram. If you can make a free body diagram, you can do a force problem. Questions? Okay. The next problem will be conservation of energy. Now, energy has a whole lot of terms. For the record, 3 people skipped this energy problem. And I can say energy, let's just zoom in on this. That energy has 4 terms. 2 for kinetic energy, 2 for potential energy. Sometimes I do rolling problems. Sometimes I do spring problems. I almost always do one or the other. This one, I'm just looking at it without reading it yet, kind of looks like a rolling problem. There's a ball on a hill and there's no springs in sight. If you want to see a spring problem, go back, take a look at what I did in class, me on a pogo stick. On the practice problem day, I did Sonic the Hedgehog. And on the homework, it was Mario. There was also one with Min Min pushing someone to the side. And on the homework, I want to say it was Monkey D. Luffy flinging someone. Go through, look at problem 5 for springs. But for rolling, we covered that actually in chapter 8. But the idea, no matter what, conservation of energy, which will be number 7, is all going to be based off that the energy at one spot equals the energy at another. Now, in this problem, I say, in Jurassic World and its immediate sequel, characters are ride around in a gyrosphere, clear hollow ball to absorb the poke. The gyrosphere was at rest at the top of a hill. It was allowed to roll solely by the force of gravity and no force from the engine. What's the velocity at the bottom? So I'm comparing two spots, the energy at the top and the energy at the bottom. Once again, conservation of energy, E top equals E bottom, or springs maybe EA equals EB or something. That will be part of it. And what I'm going to do is I'm going to take my 4 terms of energy and figure out which ones I need. Now in this one, there is no spring. So I'm just going to move that out of my area. Say, I don't need that. There's no spring. If there is a spring, there's no rolling. Get rid of the 1/2 I omega squared. And I'll say at the top, it starts at rest. That means the energy at the top is just potential. At the bottom, it is rolling. If something is rolling, it's doing 2 things at once. If something is rolling, that means it's moving linearly and it's spinning. And so I need both of those terms. But on those terms, I is the moment of inertia, and I gave that here. I said treat it as if it's a hollow sphere, which is 2/3 mr squared. And omega, anytime something's rolling, there is a relationship between the speed it spins and the speed it moves. That relationship is that omega is V over R. 3, 3. And so if it's omega squared, I can say it's the same as V squared over R squared. This allows some 2's to cancel out. This allows some R squares to cancel out. And you get 1/2 mv squared plus 1/3 mv squared, which is 3/6 mv squared plus 2/6 mv squared, or 5/6 mv squared. And if E top equals E bottom, that means E top equals E bottom. Once again, your energy problem might not involve rolling, might involve springs. Go back, take a look at spring problems. We did a few. Any questions? Okay, it is pretty close to 1 o'clock. I'm almost at an hour. I am just going to keep going anyways. If you have to go to something else, feel free to just log off. The video will be posted. Takes a long time to do problems out loud versus doing it on paper. The 8th problem will be conservation of momentum. The nice thing about conservation of momentum is, well, there's a few nice things. One is it's going to be the easiest problem. The second is there isn't much there. Conservational momentum has very few steps and very few equations. And so when you get to problem 8, which will be conservational momentum, you know it's going to involve initial momentum equals final momentum, where momentum equals mv. I can give you 10 points out of 25 for that without even looking at the problem. For the record, no one skipped the momentum last year. Now, what I do with this problem can change. I might go left, right. I might go up, down. I might go that they bounce off each other, so the two things collide and go off. Look at the hockey players that was on the homework. Or I might do completely inelastic. In completely inelastic, the two things get stuck together. Practice ones where they bounce off also, but this one is completely inelastic. And it says, the Doom Slayer, the character from Doom, jumps at a speed of 16 meters per second. So velocity of Doomslayer initial of 16 meters per second. And grabs onto a cacodemon, type of floating spherical demon, who is floating at 12 meters per second. Now here's the biggest mistake people make on these. Watch your directions of vectors. Momentum is a vector. We are going to define everything to the right as positive, everything to the left as negative, up as positive, down as negative. The way I drew that picture, that cacodemon is moving to the left. So I have to say this is negative. The text doesn't say it's negative. I just say floating towards it. The picture says it's negative. The picture is all important. Right after the Doomslayer grabs the cacodemon, what's the pair's velocity? Please put magnitude and direction, and I give the masses. What I would say is initial momentum equals final momentum. That means the momentum of the Doomslayer, which is mass Doomslayer, velocity of Doomslayer initial, plus the momentum of the cacodemon, mass of the cacodemon, velocity of cacodemon initial, is their combined mass, because they're combined V final. So I'm putting on the points. 3 for the negative sign, 5 for this. And I'll just divide both sides by everything in parentheses. Now, one thing on these problems. I always say, what is the magnitude and direction? I was pretty explicit on this one. Please put magnitude and direction. When I say that, I actually want to write out what the direction is. So the value is 0.259 meters per second, and it's negative. Negative is to the left. I literally just spelled left wrong. Once again, I might not have them stick together. If they don't stick together, trying to remember what we did in class and practice problems. In class, we did Wolverine and Magneto. On practice problems, there was a Shuriken from Street Fighter. There was another one too, but I forgot what it is. Any questions? Okay. The last problem is traditionally the most skipped. I don't know if that's people just get to it and freak out and don't want to do it, or if it's just, people just work through the beginning and just don't do the last one. Last time 17 out of 22 people skipped this problem. So take that as you will. But the last problem will be rotational. And rotational can go a lot of places. Rotational has the link between linear and rotational. It has the kinematics. It has centripetal acceleration. It has torque. It has angular momentum. And just like how the last two problems on the last exam kind of had a mixture of things, I'm going to be doing that in just one problem. I'm not going to cover all of these topics, but I could do anything within them. And I did a problem on this for you guys too about the same scene. Didn't realize. It's hard to tell you how to study for this one because it could be a whole bunch of stuff. The kinematics almost always show up. I would expect the kinematics. Anytime anything gives you a angle in radians or revolutions or a time, that's kinematics. We did a lot of problems. All the problems in 7, all the problems in 8, we can use them to study. But let's actually do this. At the very beginning of the first Guardians of the Galaxy, Star-Lord tosses an orb holding a power stone to the Kree Korath. The orb can be treated as a solid sphere with a radius, is that a good height? Yep. Of 0.0575 meters. I actually measured the radius because I have a thing of this that came with a DVD collection. And a mass of 3 kilograms. The orb hitting the ground applies a force of 8.25 newtons at its radius at an angle perpendicular to the radius, as shown below. What is the angular acceleration? Okay. I give a moment of inertia. Well, I gave a moment of inertia. If I give a moment of inertia, that kind of narrows down equations. Because I say if I give a moment of inertia, I probably need to use the moment of inertia. That doesn't show up here. That doesn't show up here. That doesn't show up here. I also gave a force. So I'm going to look at those ones with forces and moment of inertia. And I can say, hey, take a look. Torque, which is RF sine theta, is also I alpha. And I gave really 3 equations for saying this is torque and 3 points for that is torque. That means the angular acceleration is just RF sine theta over I. Or in this case, RF sine theta, but the sine of 90 is 1 over I. I can cancel out an O if I so wanted. And rearrange a little bit. Actually, you know what? I actually did it differently. Oh, that makes sense. You know what? I would do it slightly differently. I actually just went and solved for I. I also changed from 2/5 to 2/3 here by mistake. But since I just crossed out, it doesn't matter. I'm getting ahead of myself, but I'm going to need the I later on. So I might as well just get it. And so alpha is all F over I, or 0.0575 meters times 8.25 newtons over I. Assuming the orb initially spins at 4 revolutions per minute. Okay, revolutions per minute. If you see anything show up with revolutions, you're going to have to convert it. We know 1 revolution is 2 pi radians. I'm not going to give that conversion. You should know it. You also know, and this one I assume you know, that 1 minute is 60 seconds. And so if this is initially spinning at 4 revolutions per minute, that means it's initially spinning at 418.879 radians per second. Now also said it was initially spinning. So that's omega naught. So if it's initially spinning at that, my constant, what's the angular velocity at the orbit? 2 seconds. Well, take a look. I gave a time. If I gave a time, this goes back to what I said before. If I give a time or angle, that is kinematics. So I'm going to go back up to my kinematics and say, I know time, so we can get rid of the one without time. It's going to be one of these. I say, what's the angular velocity? That's only in this one. So I'll just say omega equals omega naught plus alpha t, or 0.418879 plus 120 radians per second squared times, say, 4 seconds, 2 seconds. Really? Oh, yeah, that makes sense. Because it's going to be 120.418. So because of rounding, it just looks like that. Part C. At this point, what's the angular momentum? Well, that's really obvious what equation. There's only one for angular momentum. L equals I omega. I stopped putting points down at one point. Plus 2, plus 2, plus 3, plus 3, plus 5. Now, once again, this is the hardest one probably to study for. It's probably why so many people skipped it. So it's the last one. But the thing is because I'm putting a lot of topics in one, it's normally one of the least complicated. The first one is going to have pull from this free body diagram and put it together. Because I'm going to be trying to put a lot of topics, I'll usually have multiple parts. This has ABC. That's pretty common, which means they'll all be like an instant thing. Just plug into equation. Just plug into an equation. So it will probably be one of the simpler problems. I won't guarantee it. I don't remember what I put on the exam. I wrote it a week ago, but that was usually the case. So that is last semester's exam. Your exam will not be the same, but it'll have similar topics. And I think I've probably given enough hints over the course of this time to kind of give you an idea of some stuff that might be there. Practice old problems. I highly recommend practicing. The example problems we do in class on Fridays are great things to example, or going back to homework. I've given a link before to a online textbook that I wrote that's just problems. They're all old exam problems. If you email me, I can give that link again. It doesn't have solutions, but I have the solutions. I won't give them to you, but I can tell you if you're doing things right or not. Any questions before we go? Okay. Those of you watching this on YouTube, assuming anybody watches on YouTube, my YouTube views are really crap. If you have a question, you can always email me. Other than that, we have class tomorrow. I got office hours today. I hope this helped someone somehow in any way, and have a good day.